Welcome to my video lecture. I'm making this video for my programming languages and compilers course. This course consists of 3 parts. The first part is about compilers, mainly the front end of a compiler. The second part is about programming language paradigms. It covers functional programming and constraint logic programming. The third part is about runtime systems. This lecture starts the second part. So we are going to begin with constraint logic programming because it has a good connection to the previous part. So we are going to learn constraint logic programming through the Picat language. So I'm going to use the web IDE for Picat, implemented by Alexandra Silva. So we're going to take a look at 2 examples. The first example is a simulator of a finite automaton. So consider this, consider regular expressions over this language, over this alphabet, okay, A, B, and this regular expression A or B, closure and A, B, B. This regular expression matches any strings that end with ABB. So we can easily design an automaton for this regular expression. Okay, so begin with the start 0, state 0, and then we have ABB. Okay, say 1, 2, 3. Okay, so in state 0, okay, on input A, okay, we either stay in state 0 or move to state 1. And in state 0, on input B, we stay in state 0. Okay, so here, and from state 1, alright, to state 2, okay, we need a B. And from state 2 to state 3, okay, we need another B. Okay, so we will come to the final state, state 3, if the last 3 characters, last 3 symbols are A, B, B. Okay, so now let's write a simulator of this automaton. Okay. Alright, let's name the predicate FA, okay, standing for finite automaton. This predicate takes 2 arguments. The first one is a list of input symbols, and the second argument is the current state. So if the input symbol, the list is empty, and the state, and then the state must be a final state. Okay, if the this is a first symbol, and this is a the rest of the symbols, okay, seems this is the current state. Alright, so we make a transition. Alright, so in state on input sim, we move to a new state. Let's call it next state. And from there, okay, we continue. Yeah, sims. Alright, so this is a simulator. Okay, basically, it finds a path from the start state to a final state that where all the arcs are labeled by the input symbols. Alright, now we need to encode an automaton. Alright, so we write this move. So this move. Alright, so in state 0, okay, on input A, we stay in state 0. And state 0, on input A, we can also go to the next state, a different state, state 1. Alright, this makes the automaton non-deterministic. And state 0, on input B, okay, we stay in state 0. And in state 1, alright, so B, okay, we move to state 2. And in state 2, alright, if we see B, alright, we move to state 3. Alright, and so this encodes, okay, this automaton. Alright, so this relation move is define a bunch of facts. Okay, we need to declare how the facts are indexed. So the index is indexed this way. The first one is input, the second one is input, and the third one is output. And the final state, okay, so this is final. Okay, state 3 is a final state. Alright, good. Alright, now okay, we write main predicate to test it. Let's say FA. Okay, the input is A, B, A, B, A, B, B. And the initial state is state 0. Okay, also we want to print out something. I say print accept. Alright, good, accept. Alright, we run. Oh, it says error, something is wrong. Oh, okay, well, because this one. Okay, try again. Okay, accept, it runs. Alright, so I give you an exercise. Okay, this one encodes these strings that end with ABB. Alright, consider running this simulator on an automaton, okay, that accepts strings that contain even number of A's and even number of B's. Alright, good. Alright, now let's move on to the next example. We want to write an evaluator of expressions. Okay, so this is a famous grammar. An expression is defined as an expression followed by plus followed by a term, expression followed by minus followed by a term, or okay, just a term. And a term, okay, is defined as a term times a factor, or term divided by a factor, or a factor. And a factor, let's consider, okay, because we don't want to write a tokenizer, so let's assume all the operands are digits. Okay, so a digit or expression, okay, this good. Alright, we if you remember, we wrote an evaluator in Java a while ago, and that program was pretty long. Okay, so now let's do it, okay, in Picat. So, well, basically it is a recursive distance parser. For each non-terminal, we write a predicate. Okay, so for parsing that non-terminal. Right, so for expression, let's write a predicate called exp. This takes 3 arguments. This first one is a list of input tokens. The second one is a list of output tokens. Output means tokens that are not consumed. And also value, that is value to be returned. So we make this non-deterministic, because we don't know which rule to choose. Good. And so this is we encode this productions. Well, actually, we can rewrite this one as this is E plus, this E plus T, or minus T, or just a T, So this is, alright, we commented this out because this is not part of the program. Expression SI, let's say the output from this one is S1 and the value is value 1, and let's say the next one, SI S1 equals, alright, there's a token after this, let's call it OP, good, and S2, and S1, SOP is either this is a plus or OP is minus, good. And after this, what do? We expect a term. We expect a term. So S2, and the output is SO, and then it's value 2. Alright, from value 1 and value 2, we apply this operator on these 2 operands to obtain a value. So there's a built-in code apply, so let's name this one my apply. So this is apply operator, value 1, value 2, so this is a function. We could define this as a predicate, so, alright, let's say it's a function. Value equals my apply, good. Alright, so this is the first 2 productions. The next, alright, we do this is one remaining production. An expression is defined as a term. Alright, so term. Alright, so we can encode these production rules similarly. So a term is defined as a factor. So a term factor. So this one output is S1 and the value 1. Good. And after this, we expect an operator. S1 equals OP. Alright, S2. And this OP is either multiplication or division. And then after this, we expect a factor. Factor. Good. So this is S2, SO, and value 2. And then we use my apply. So we use my apply. And there's one more production. So a term SI this one is okay, just a factor. Oops, factor. Okay. All right, now let's encode these productions for factor. Okay, so a factor is factor all right. So let's say the first input symbol. Okay, this is token. Okay, you set token. Si. All right, if it is an open parenthesis. Okay, let's say if it is an open parenthesis. All right, token is open parenthesis. Then what do we do? All right, then we can do it deterministically. It is we need an expression. We need an expression. Okay, and this is S1, and the value is value. Okay, and after this we expect a closing parenthesis. So S1 equals closing parenthesis and SO. All right, and the factor. Okay, so this one is okay. It's not open parenthesis. Okay, these pattern matching rules are very convenient. So it is token. All right, then okay, we expect a digit. Okay, expect a digit. So this is okay. Let's call it ASCII digit. This is a built-in token. It's ASCII digit. All right, then what do we do? Okay, then what do we do? All right, then SO equals SI, and this value equals. All right, we converted this digit to integer. Okay, to integer, we use this built-in function order token. Okay, and minus order 0. Okay. All right, good. So basically, we have finished. Okay, translating this grammar to a Picat program. Okay, it is very straightforward. It's not surprising because Picat is based on Prolog, and Prolog was initially designed for natural language processing. This program doesn't run. Okay, why? Because of the existence of left recursion. Okay, in order to stop it from looping forever, okay, we need to declare the predicates left recursive programs tabled. Okay, this one is also left recursive table. Okay. Oh, we also need to define this myApply. Okay, myApply. Its operator is x. Okay, so this is a plus x, y. Okay, this is x plus y. And minus times and then division. Okay, so it is complete. Okay, now let's write a main predicate to test it. Let's say expression. All right, this is expression. This is let's say 3 times 2 plus 4. Okay, and of course after this, okay, we don't have any tokens remaining. Okay, so this is a value. Okay. and then we print ln value. Alright, so make sure everything looks good, because this online web IDE, unlike a local compiler, it's not so user friendly because it does not give you all the error messages. Okay. Alright, let's run. Alright, so it is successful. Okay, and alright, now it's an exercise. Okay, this program uses tabling. Yeah, okay, you see this, and we know, okay, we can easily transform this grammar into one that does not contain left recursion. Okay, so if you remember, okay, the grammar looks like this. Okay, this is a term in E prime, and E prime is defined as epsilon or plus t and E prime, or minus t E prime. Okay, similarly, okay, we can also transform other productions to eliminate left recursion. Alright, here's an exercise. Alright, write an evaluator based on this transformed grammar. Alright, since this transformed grammar does not contain left recursion, so you don't need to use tabling. Okay, tabling is nice because okay, you see, okay, makes your program declarative. Okay, it's declarative and it runs, but okay, it does not mean it has no overhead. It has overhead because everything is tabled. That means, okay, your program consumes space. Okay, so the exercise is, okay, write an evaluator based on this transformed grammar. Okay, that does not need to use tabling. Okay, so that's the end of the first lecture. Thank you for watching.